Well, hello there, and welcome to Mechatronics. So this first lecture is going to talk about the basics of getting started with a mechatronics project. We're going to hit the ground running with some Arduino software development right in the beginning, but this presentation is more about how to plan a project so you don't hit any snags. One thing that you'll find is if you ever took Circuits Lab, for example, and you built a circuit on a breadboard, it probably didn't work the first time. It's very easy to make small mistakes and you have to check your wiring. So anytime you're building hardware, it might not work. If you took a programming class and you wrote a computer program, it also might not work the first time. It's very easy to have bugs in your code. So with those two things, it can be very frustrating to get a mechatronic system that has both a circuit and a program to work the first time, to do something, to turn the crank. So using example programs so that you have a tested program to use, or using the board in a way that you've tested before, trying to minimize the number of things you're testing at once is the main goal here. So this step-by-step process is one that I've used for developing mechatronics things, and the idea is to first make some plans on what hardware, what we're going to connect up to the Arduino or the microcontroller. So plan our inputs and our outputs, which pins we're going to use. Plan the peripheral use. Peripherals are things like analog to digital converters and serial ports. You might only have a few of those, or not every pin can do every job. So make sure you're using the right pin for the job and you're not trying to use the same pin twice or something. The third step is to draw a schematic so that you've got a circuit diagram of what things are going to go where, and you can assemble it if you're having to solder it together later, and just so you know how to connect all the connections. Then you can turn to the software, but you want to start with the simplest software that you can test. So write a skeleton code, a very simple code, doesn't have all the fancy features, basically tests the inputs and actually run it with just the inputs, no outputs. See if it can read the voltages or talk to the sensors, whatever it's going to do, and print them out. Then drive the outputs. See if you can run your speaker or your motors or your LEDs, whatever it is. Make sure that part works. And have the simplest code that exercises all of the hardware that you can fall back on if things don't work. You can see, well, is my basic skeleton code working, and give you some confidence in where your bugs are. Once the hardware is set up, then you can write your control code, your big software program. This is often very time consuming and you have to do a lot of testing. So I like to get the whole hardware set up with a skeleton code first. So a mechatronics program, a microcontroller program, is different from a program that you might write in MATLAB or something like that for a PC. The main thing is that a microcontroller normally just has one program that it runs. So you program the microcontroller, you turn it on, it runs the program, and it never stops. Think of something like the controller that's opening the doors at a supermarket. You power that thing up and it waits for someone to walk in front of the sensor, opens the door, when the people are gone, closes the door. You don't want it to finish. It's never going to go check its email. It has one job and it does it over and over. So the typical code flow is in this drawing here. So there's normally some initialization when you turn it on. It'll set up the sensors, storage, anything like that, and maybe some setup. If you've flown drones, you turn them on and leave them still so that they can measure the acceleration and calibrate themselves. Sometimes you have that kind of a thing. Stuff that happens when you boot it up or turn it on. After that, it's going to jump into the main control off, looking for the people and opening the doors. And when it's done with that, it's going to go back and do that again. It looks for people. If there are people, it opens the door. Otherwise, it looks for people. There's people, it opens the door. So most microcontroller programs have an infinite loop because they never stop working until you just turn them off. They don't exit and do a different program. There's only the one program. So normally an infinite loop is something that you do by mistake in a program like MATLAB because you can't check your email while MATLAB is stuck in an infinite loop. But you want one for the microcontroller. Sometimes there's an exit, but most of the time there isn't. Okay, so let's look at those steps in a very simple example with the Blinky Arduino program that you've probably run in one of our labs already. So the Blinky Arduino program needs to blink an LED, so that the I/O, the input-output, it's going to have one output pin that we're going to connect to an LED. So we need one light. We have to decide where it can be. So any of the digital output pins will work to light LEDs. They can be on or off, and that's all we need. So these are the digital pins on the top of this picture of the Arduino. Analog pins down here. You can also use those for digital, but that's their second choice. And you never want to use these serial ports, TX and RX. They're used to program the chip over USB. So don't hook your LED up there, or it'll do funny things when you try to program the chip. So any of these 2 through 13 would be good choices. We're going to use pin 13 because it actually has an LED already built in to the board, so we don't have to wire it up, although we could if we wire this up to pin 13 and ground. This LED will light at the same time this little L LED will light, because they're both hooked up to the pin. And we can draw the schematic. So pin 13, resistor, LED, and back to ground. So we've made decisions on how we're going to hook up the hardware. Now we need a skeleton code so that we can run and test things out. This is a very simple program. Often you might start with Blinky as your skeleton code because it's a very simple thing, and if Blinky doesn't work, you've got serious issues. So this is going to be the skeleton and the program all at the same time. But just to sort of see how it works, remember, Arduino has 2 functions always in its program. One function named setup, that runs once when we boot the microcontroller, when we power it up. And then there's a function named loop, and loop runs when setup is done. It jumps to loop and runs loop, and when loop is done, it jumps back and starts loop over. So the Arduino inventors decided this was the right way to do it. This is unique to Arduino. It's not standard C to have a setup function and a loop function, but it fits this model that everybody's been using since way before Arduinos, where you have a setup and initialization and then a loop afterwards. So the setup function in the Blinky makes our pin, which could either measure voltages or drive voltages. We have to tell it which mode it's going to operate in. So we set pin 13 to be an output. That means it can turn on and off. And then in the main loop, we're turning the pin on. High means set it to 5 volts on most Arduinos. Pause for 1 second, and then turn it off. Low is 0 volts on Arduinos. And then pause for a second. So on, pause, off, pause, start over, on, pause. So it's going to blink that LED until you turn it off. And if you power it off, plug it back in, it's going to start blinking the LED. That program's stored in the permanent flash memory. So that's the mechatronic design process, the steps to think through when you're making something new. Just a little bit more complex example before we finish up here. Looking at all of the pins on an Arduino Uno, like this one shown here, sometimes you will buy these things called shields that stack on top of the Arduino to hook things up. A shield is an Arduino specific term. It's really a daughter board. Motherboards and daughter boards is another way to call these. Everybody seems to come up with their own name. So they're shields for the Arduino ecosystem. And they stack, the pins stack into these pins so that you don't have to do any wiring, and you can actually stack multiple levels if you want. So that's what happens sometimes is you have 2 shields. So here are 2 shields that you can buy. These are pretty old designs. This first one is the MP3 player shield from SparkFun. And it has a little place for a micro SD card and a headphone jack or speaker output, and it will play sound. So people use these for their Halloween decorations and things like that. So it has these pins that it's using to talk to the Arduino. So it has to use all of these pins, and they're labeled here on the board. So these pins are taken up by the MP3 player shield. And so what you might happen is you want to do this, use this to play the sounds, and then maybe you want this is the Arduino board, which is an L298 board. Like, we're using a slightly different board for the class. Most likely you didn't buy this one. But this is in shield format with that motor driver chip. And if you stack these on top of each other, if it used to work, it won't work anymore. So if you tested out your sound and then add the motor, it's not going to work. If you test out your motor and then add the sound, when we stack these on top of each other, they don't work. So this was an old midterm question. Why doesn't it work? And the reason is here. If you look at the pins, these are oriented differently, but this notch here corresponds to this notch here. The motor driver board needs pins 11, 12, 13, and 3. Just needs these 4 pins. And the MP3 player is also using 11, 12, and 13. So if we try to use these at the same time, when we send motor commands, it's going to break the MP3 function. When we send MP3 function commands, it's going to drive the motors and do weird things. So I've seen this before with students. This is a very common motor setup. And remember, pin 13 is the blinking LED, so sometimes people will be debugging their code and they'll say, well, when I sense something, I'll have the LED turn on. And the LED turns on, but maybe their motor is turning on too. So this is a difficult one to fix if you're actually stacking the boards. The fix for this would be to use different pins for the motor board. So use some of the pins that aren't used by the MP3 player. And you'd have to either not stack these, you could wire them separately, you could solder wires in here and then add them onto the Arduino yourself, or you could cut the traces and move them around or something. But when they're built and designed like this, it's a little harder to fix, but not impossible. That's one of the biggest frustrating things people come across in the Arduino, is you find an example of half of your program. You want to run motors and play sound, so you get the sound playing working, you get the motor driver working, and then when you combine them together, you have to really understand what they're doing in order to figure out why it didn't work. Alright, so that's the basics. Remember the step-by-step process for mechatronics development. Testing small changes and having things to fall back on when it stops working will really save you some frustration. Alright, I'll see you in the next video.